Okay, so welcome again to our data science program. So in our today's class, we want to proceed with our machine learning tutorials, where we had actually introduced the data science program, and then we made an introduction to machine learning. And now from there, we introduced the two types of machine learning, where we said we have the supervised machine learning and the unsupervised machine learning. So in terms of supervised machine learning, we mentioned that we have the regression models, which we did on our previous class. And basically, we had said that regression models deals with numerical outputs. Now, in our today's class, I want us to proceed to the classification models as a supervised machine learning technique. So in an overview, we can now say that classification is a supervised machine learning technique where it is mainly used to predict categorical outcomes, the most important element, in such a way that we are saying that categorical outcomes are basically textual outcomes. So like we had mentioned earlier, that regressions focuses on predicting numerical outcomes. Now with classification, we actually focus on predicting categorical outcomes. In other words, they are normally called the discrete labels. Regression focuses on continuous labels. Here we are focusing on discrete labels based on the input features. So therefore, it involves training a model using a labeled data so that now we can use it to assign new unseen data point to the predefined classes. Okay, so we can actually evaluate classification problem using different metrics like accuracy, precision, recall, and F1 score. So we're going to learn this aspect practically in our codes. So if you're doing classification, basically these are the key characteristics. So the first one is that it is a supervised machine learning technique. Therefore, it requires labeled data with input-output pairs. So remember, in contrast to unsupervised learning, where we don't have labels, okay? So that is the first characteristic of classification machine learning. And also, very importantly to remember is that classification, the outputs, the labels are basically discrete categories. So in other words, we are mainly focusing on predicting categories that are that are textual in nature. For example, I want to predict whether a patient is diabetic or a patient is not diabetic. So we can use this one for disease diagnosis. I want to check whether an email is spam or not spam. Or in another example, we can even say, I want to check whether a transaction is fraud or not fraud. So we can also use it in aspects like fraud detection. Okay, that is very important to remember, is that the outputs are discrete categories. In contrast with regression, where we said they are continuous. So mainly they are numerical in nature. So we have several types of classification. So we have a binary classification in such a way that we are only predicting two classes. For example, I want to see whether a patient is diabetic or not diabetic based on the input features. So we can also do multi-class classification. So for example, this is whereby the outcome is more than two. For example, a good example is the iris prediction, where we actually group three different flowers species. And we also have multi-label classification, where we have multiple labeled per instance. So we're going to check on these types of classification practically in the codes. So in terms of the common algorithms that we used in classification, a good example is logistic regression, where in regression, we were saying we actually work with linear regression. So please let's keep that one in mind, that regression, we focus on linear regression, but here on classification, we mainly deal with logistic regression. From there, we also have other algorithms like decision tree classifiers, We also have random forest classifiers, support vector machines, k-neighbors, gradient boosting, and we can even do it in a deep learning technique using the neural networks. So the most important aspect here is to remember what is the idea behind decision tree? How do you implement decision tree? How does the random forest work? How do you implement support vector machines? So that is also a very important aspect in classification. It's always good to remember about the algorithms that are used in classification. From there, we also have to remember about how can you evaluate a classification model. So we remember with regression, we had said we work with the R2 score. Here with classification, we mainly focus on the accuracy score, but you also have other evaluation metrics like the precision, the recall, the F1 score. We also have the confusion matrix. Sometimes we use the receiver operating characteristic. It's like the ROC curve or area under curve. And also we have the log loss. So the most common ones are the accuracy. You also have the confusion matrix, precision, recall, F1 score, and classification report. So for this class, I had picked a case study where we are going to implement it using Python, where I wanted to implement a case study for diabetes prediction using the PIMA Indians diabetes dataset. Okay, so this is actually our case study. I think the code is already, the link to the Colab is already here. So let's first open the link. Then now we explain a step-by-step procedure that we are going to follow on implementing this classification model. So if you open up the link that I've shared here, you are going to land into a Google Colab notebook where we have implemented a diabetes prediction model. So let's first understand it theoretically, then now we are going to implement the codes. So it's actually very, very similar with regression, only that now we are predicting categorical outcomes, okay? So in this case study, as you do any case study project to do with machine learning, you need to have an objective for that project. So for this project, our objective is to predict whether a patient has diabetes based on some medical features. So these medical features, we want to use the PIMA Indians diabetes datasets. So very importantly, as a machine learning engineer, it is always important to understand the dataset that we are using here, the PIMA Indians dataset. So this PIMA Indians dataset, you can actually get it from Kaggle. It is available on kaggle.com. Remember, we had talked about Kaggle in our introductory classes. So Kaggle, very important. So you can actually get it here from kaggle.com, download it and upload it to your repository. From there, we also have the UCI machine learning repository, okay? So these are the sources of the dataset that we are using here. Now, the description for this dataset is that it contains medical records for PIMA Indian women. So these women were aged above, they were actually 21 years and above, okay? And these PIMA, people of PIMA Indians comes from the area of Arizona in the United States. And the goal of this data is to predict diabetes onset. So one constraint about this project is that it can only be used by women. I hope you can see that one, because it was mainly for women, and they should be above 21 years of age. So the data that we're actually using contains the 8 input features. So these are what we call the independent variables. If you actually recall our introductory machine learning classes, these are the independent variables. So these are the inputs. These are the medical records that you want to use. So with these features, we want to know whether a patient is likely to have symptoms of diabetes or not. Okay. So the first feature that we were checking is the pregnancies, or the number of children that the woman had. So the number of times a woman got pregnant is actually a feature that can determine whether this patient can develop signs of diabetes. We also have glucose, in such a way that glucose is actually the plasma glucose concentration. It is measured in 2-hour oral glucose tolerance test. Okay. From there, another feature that we have is the blood pressure. So it is a diastolic blood pressure measured in millimeter pressure here. Then from there, we are also checking the patient's skin thickness, okay, measured in millimeters. We're also checking the insulin in such a way that it's a 2-hour serum insulin. You also have the body mass index. And if you want to calculate the body mass index, it's actually the weight of the patient in kilograms. You divide by the height squared for that patient in meters, okay? Now from there, we also have something we call the diabetes pedigree function. So pedigree function is actually, it focuses on genetic risk score, like the family bloodline. If you had, maybe let's say you have an uncle or you had a brother, so this could determine whether you're also likely to have signs and symptoms of diabetes, very, very important. And finally, the age that you want to measure in years. So based on this project that we're doing in machine learning, we are actually feeding the 8 features of the patient so that now we can have the target. So our target is the outcome, which is binary, whereby we can say that the patient is non-diabetic, representing it by 0, or the patient is diabetic, where we can represent that one by 1. So this is what we call label encoding, okay? Where 0 can represent a patient without diabetic symptoms, and 1 representing a patient with diabetic symptoms. So in this data set that we're using, it's also important to know the number of records that we had. So we had a total of 768 records, okay? So then it's also very important to check the distribution. So approximately 65% of the records are for patients that are non-diabetic. So this problem is biased on people who are non-diabetic, and 35% is for now the patient who are diabetic. So this one is actually indicating that our data set is slightly imbalanced data set. So later we are going to see how you can balance your data set so that now your prediction is not biased on one aspect, okay? So after getting the data and understanding the data set that you want to use for this project, what is now the methodology? How do you start? I think we also did this one in our regression. The methodology for supervised machine learning is always the same. So the first thing you have to do is we have to start with data preprocessing, where it focuses on ensuring that we are working with the correct data. So how do you ensure that is possible? You can actually handle missing values. So we have several ways of handling missing values. We can replace them, or we can actually drop them, okay? We can even check whether the data contains some outliers. We can do feature scaling. We can now talk about test train split, and we can also handle imbalance. This is something we're going to do later because you actually saw that our data is slightly imbalanced. So there is a procedure called SMOT, which is actually the synthetic minority oversampling technique that is mainly used to balance classes in the training set. So this is actually a very important aspect in any machine learning engineer, ensuring that you're working with the correct data. Now from there, the second methodology here is what we call model selection. So with model selection, this phase, we actually ensuring that we are working with the correct machine learning algorithm that we normally call them model. So we can actually either pick logistic regression as our base model. We can work with random forest. We can work with XGBoost. So for us to ensure that we picked the correct model, we normally test a technique that is called cross-validation. So with cross-validation, we are going to go through all the models, all the algorithms that I had mentioned, and we pick the best algorithm that we are going to use for training our model. That is the second step, very, very important. In our third step, we now go to training. So with training, we will actually fit the training data. I'm going to show you that one. And then now, based on the algorithm that we picked here. So we are going to actually pick the algorithm here, and then now we fit in the training data. And now with that one, we can say that now the model has learned from the data. So there are some aspects that we can monitor, like the learning rate, the number of estimators, and so on and so forth. Okay. Now from training, it seems that now we have a model that can predict whether a patient has diabetes or not. From there, now we can proceed to evaluation. So with evaluation, we can actually now check the accuracy of our trained model here. And then now finally, these are other optional steps, like actually checking feature importance. So in this manner, we can actually analyze the coefficient to identify the impactful features that we can use for this project. And now we use, finally, we can now deploy this model in either in a cloud platform, so that now we can use it for our day-to-day prediction. Okay, so in this manner, we can use the best performing model to predict diabetes for the new patients. So I want us to go direct, implement that code practically using Python. And then out from there, we are going to come back here and now check some of the real world applications of classification as we now end the class. So let's go to the project and then explain the methodology. So for actually working with the data, like we had done in our exploratory data analysis classes, we had mentioned about NumPy. Let me enlarge my screen here a bit so that you can see. I hope you're able to see that one. So we need NumPy, we need pandas, we need matplotlib, and we need cbot. So these are data preprocessing libraries that we have imported. Now from there, we can now read our diabetes data using the pandas.read CSV function. So this is a function that you can get from the pandas library. And then now you provide the link to the dataset. So this link, it should indicate where your dataset is hosted, or basically you can go to kaggle.com, you download the dataset, then you upload it in your project, and then you can read it here. So if you have read the data successfully, sorry for that one, you can actually take the variable and now take head. So with head function, you're actually reading the first record. Like if you put here 10, you are reading the first 10 record just to have an overview of the data set that we are using, okay? So I hope you can see that the data we have here, it is made up of 8 features, just like we mentioned in our description, where we have the children, glucose, blood pressure, skin thickness, insulin, BMI, pedigree function, and the age. So based on these 8 features, we want to determine whether a patient is diabetic or not diabetic. So this is the main outcome. So remember, in contrast with regression, the outcomes were numerical in nature. That's why we called it regression. Now with classification here, our outcomes are categorical. In other words, they are textual in nature, okay? So that is the first overview of the dataset that we're using. From there, now we can do some statistical analysis just to summarize the data that we have and get to understand the data that we're using in a more in-depth manner. So to do statistical analysis, just like we had mentioned in our EDA classes, is to call the describe function. So the describe function, so we can actually now check that, let's say the mean age, let's check the mean age is 33. So majority of the women here were around 33 years of age. Let's check the minimum age. The minimum age was 21, so the data set is correct. And the maximum age is 81, okay? So this data can be used for women between 21 years of age and 81 years of age. We can even check another summary like the children. So we have the minimum children we had was 0. So there was a woman here without a child. So it can be used even with women without children. And the maximum number of children was 17, okay? Let's check the BMI. The least BMI was 0. This could be an outlier. The highest BMI was around 67. So with statistical analysis, we are actually getting to understand the data that we are going to use for our machine learning prediction. Now from there, we will proceed to machine learning, like we had mentioned. So if you actually recall what we did on regression, we said that supervised machine learning, it's very important. First, we split the data into features that we're going to call it X, which contains the 8 features that I've mentioned, and the outcome, which is actually the target. So let me get a diagram here. Let me get a diagram here that we can use. Let me get a diagram here that we can use for this project. So I think in our previous class, we used this one. I hope you can see. Sorry, let me try open it in a new option. Looks like it's not that clear. I want to get a clear image. Sorry for that one. Then I can increase it. I hope it's visible. I hope you can see it. I hope you can see it. I'm trying to open it in a very good. A minute. Just a minute. Perfect. Yeah, I think we can go with this one. I think this is a very good explanation that we want to use as we now pre-process our PIMA Indians diabetes data set. So the first thing is that we have the full data set here. I hope you can see my cursor. So these are full data set having the total number of records and the total number of columns. So the first step is to separate the features from the outcome. So we have a total of 8 features and a total of 1 outcome, okay? 1 target. So that is the first step in machine learning. Like we also did it in regression, we'll have to split the features and the outcome. So that is where we are going to start from there, okay? So to explain this one, my diagram is not clear. I'm trying to see whether this one would be good. And not that, not really. Let's just go with the other one. Okay. So like I was explaining, we have the full data set here. So you want to split the full data set into features and outcomes. How do you do this one in Python? So to do that one in Python, we will first need to extract the values so that now we can store it as a NumPy array. Okay. So what I'm saying here is split. This will be done by extracting from the data frame and storing them in a NumPy array. So we need to get the data set, we extract the values and store them in a NumPy array. From there, the features that we are calling X is that we'll take all the records in the first dimension and the first 8 records. And then for Y, we are going to take all the records again, and then we take the last record, which is the outcome. So if you run this one here, if you run that one there, we have now splitted the data into X and Y. Now from there, I think I should run it again. Just a minute, should run it again. So we are connecting back to the Google servers and then we're good to go. Okay, so just to explain what I mean here, maybe it's not clear. If I run this part, this is the shape of our data. This is the shape of our data. Let's confirm again so that now it makes much more sense. We have a total of 768 records on this first dimension. So that you can see. So we have a total of 768 records and 9 columns. So remember, out of these 9 columns, the first 8 columns are the features and the last 1 column is the outcome. So to do this one, X, we are going to take, for X, we are going to take all the records. That's why we are putting this symbol and the first 8 columns. So if you now check the shape, let me run it here again. We have a total of 768 records and 8 columns. So these columns are what we are going to use as the features, okay? And then now, similar to Y, so if I now run this one, we have a total of 768 record and 1 column that we're going to use for target based on the diagram that you're seeing here. So we have a total of 8 records and 768, 8 columns, 768 records. Those are the features. And then the target, we have a total of 768 records and 1 target. Now from there, a very critical step is to now get the training set and the testing set. So in such a way that we are going to split this data so that we have the training set. For training, we have X train. So these features that we are now calling X, we are going to split them so that we get the X train and the X test for the features. And then now for the target, we also get the Y train and the Y test. I hope that one really makes sense so that now we can go and implement it together. Okay, so we have X train, X test for the features, Y train, Y test for the target or the outcome. So how do we implement this one here? So to do that second step, B, that I've called B in my code, that I've called B, is to now split the data set X, so the X, which is what we are calling the features, and Y into training and testing sets. So conventionally, the training set will be used for training the model, and normally it covers around 70% of your records. So like I want to assume you're a teacher, you want to train a student. So the machine learning model is your student. So you'll have to feed it with the majority of your data. So I'm assuming we can now work with 70% of the total records. Similarly, the remaining 30% will be now used for testing, for evaluating the model, okay? So how do you do this one? So we are going to actually the library scikit-learn, there is a module called model selection. So remember that was our second step. We can now call a function called the train test split. So remember, this function is mainly used to split your data into training and testing. That's why it's called the train test split. From here, we are going to get a total of 4 datasets where we have the xtrain, xtest, ytrain, and ytest. According to the diagram here, we have the xtrain, the xtest, the ytrain, and the ytest. So we have a total of 4 variables. If you split this one now, you're going to get a total of 4 variables. So to do this one, we are now creating the 4 variables, the xtrain, the xtest, the ytrain, and the ytest. And now to split the data accordingly, we are going now to call the function called the train test split, this function here, the train test split. And now the first thing we do is that we supply x so that it should be splitted into xtrain and xtest. According to the diagram, that is actually true. We supply the features that now we are calling x, these features, the ones that are in blue. Now after supplying the features x, now we are getting the xtrain and the xtest. That is the first procedure. Now from there, we now supply y, the target, so that now we get the ytrain and the ytest. Now that one is, you've understood that area. So now again, we supply y, we get the ytrain and the ytest, and now we determine the test size here, okay? So if I suggest that the test size is 0.3, now that is 30%. 30% for all the records, which are 768 records, 30% of that one will be used for testing, which means that automatically 70% of the remaining records will be used for training. And now definitely that has to be done in a random state. This means that as you're picking the number of records, you'll have to do them in a random state. Now from there, if I print my training sets and my testing sets, you are going to get that we have a total of 537 records, 8 features. This is the xtrain. 537 record, 1 column. This is the ytrain. Xtrain, ytrain. So this is what we call the training sets, okay? That is what we call the training sets. For the testing set, we have 231 records, 8 columns. Xtest, 231 record, 1 column for the y test. So it's good for me to split the two so that now we can actually, I can actually print here. So just to enhance my code readability. So basically I can call this one the training set. Just want to have some good decoration here. You can have a space here. Exactly. And then now I can also have the testing set. So if I now run this one again, I hope it's making sense that we have a total, these are the training sets, so which means that this is the xtrain, the ytrain. According to the diagram, we have here the xtrain, the ytrain. Those are the training sets. And then here we have the xtest, ytest. Those are the testing set. How that one really makes sense. And now this is what we are getting right here. Very, very important. Now from there, at least now we have the data that we want to use for our training. So another very important step is to select the correct algorithm that we can use to train this machine, so that now later it will be used for predicting patients with diabetes, okay? So the first step we do is we import all the classification algorithms. For example, here from the scikit-learn.tree, we have the decision tree classifier. From scikit-learn.support vector machines, we have the support vector classifier. In contrast with regression, we are using support vector regressor. So now here we're using support vector classifier. From there, we also have, from the ensemble, we have the random forest classifier, and also we have the gradient boosting classifier. Those are both from ensemble. From the linear model, remember the linear model, we have the linear regression that we use for regression, but here for classification, we normally work with logistic regression. We also have the k-neighbors classifier, and then from naive Bayes theorem, we are getting the Gaussian naive Bayes, a very, very famous algorithm for classification. So after getting all these algorithms, remember I had highlighted that we first need to do what we call cross-validation, hyperparameter tuning. With this process, we can actually validate and pick the right algorithm that will produce a higher accuracy. So what I mean here is that I have so many algorithms. Which one should be the best I should work with in my training phase? So to do this one, you just create an empty list, and then you append all the models with their names. So this is the name, this is the model, the name, the model. You can give it any custom name here. Okay, so you provide all the names here. And now from there, because we have, we are in a list, so we can actually work with a loop. But before we do that one, we can now import the model selection. We get the cross-validation score and the k-fold. So for every name and the model in the list of model, we are now returning their accuracy, and then we are picking the best accurate model. So after doing so, I think I should ignore warnings. So let me say import warnings. I think I've seen a lot of warnings. Yes, then I can now filter the warnings. So let me run this one again. I hope it should not take time. Shouldn't take time. So I hope you can see that with a total of how many algorithms? 1, 2, 3, 4, 5, 6 algorithms. Decision tree is scoring nearly 73%. K-neighbor scoring around 72%. Linear regression scoring, logistic regression, scoring nearly 77%. Naive Bayes is around 75. Random forest scoring 78%. And then finally, gradient boosting scoring around 76%. Okay, now from cross-validation, we can actually see that the best algorithm we can work with is random forest, because it's scoring around 78%. So it's actually the best performing algorithm for this data set that we're using here. Now from there, I think for this one, we had picked, I think it's nearly close to logistic regression, because logistic regression is scoring around 77%. Now from there, I think we can pick either we go with logistic regression or random forest classifier. So for this problem, we've picked logistic regression. Okay, now I think I can basically pick, yes, let's just pick that one. So we pick the logistic regression algorithm after doing the close validation. And then out of that one, we now feed, so we supply our training set. So remember, the training set is we have the X train and the Y train. And then from there now, we are going to get a model that has gone through our diabetes data set. So what has happened here, to clearly understand, is that we are going to give the model the features and the patient. We are saying that if you see the following features, this patient is diabetic. If you see these other features, the patient is still diabetic. If you see the other features, the patient is not diabetic. So what I try to mean here is that we supply the features, what you're calling the X trend, and the outcome, which you're calling the Y trend. So the model will go through all the record and then gain that knowledge, or sometimes you call it expertise, in the data that we have here. Now from there, it is very, very important we evaluate the accuracy of the model that we've done here. So to do this one, we now go to testing. So what I normally do here is that in the training phase, I was applying the features and their outcome. So here I will only supply the features. So I will only supply X test. I hope you can see that one. And then generate the model prediction by hiding Y test. So I only supply X test. And that is what is happening here. I hope you can see that in my prediction, I want to take the model to predict X tests and then generate its own predictions. This prediction, I want to counter check with Y test, which is the correct answer. So if you run this part here, you can see that in the first instance, the model said that, I think it should be, I think it should, let me just confirm. That's very, very long, so many records. So the first instant, the model said that the patient was, just confirm a minute, the patient was not diabetic. In the correct instance, the answer was not diabetic, and so on and so forth. So it is mainly very important to do it in a more scientific way, what we are now calling the accuracy score. So the accuracy score is actually the ratio between the correct answer, Y test, against the model prediction. Okay, so this accuracy score, we can actually import it from the scikit-learn.metrics library. So from here, we can actually now generate the accuracy score. It's actually the ratio between the Y test and the model prediction. And now after doing that ratio, we are being told here, just confirm, we are being told here that the model accuracy is, let's just confirm, so it should be somewhere around where we had cross-validated. So it's actually around 74%. I think I can try with, let me try using gradient boosting. Let me work with gradient boosting classifier. Let me work with this one. So I just need to run this one. And then let me see the accuracy. So the accuracy now is around 75, so not that bad. So this 75% we are getting is because our data set was imbalanced. So after doing what we call SMOT, we can now balance the data set and get a very higher accuracy. But for now, because now we have a model that is 75% accurate, I can now show you how you can make your own predictions, okay? Can make your own predictions. So to do this one, then remember, for you to predict the result, is that the model was trained on 8 features. So we had children, glucose, skin thickness, and so on. And then now we are targeting one outcome. So we can actually now install some new features, and then we get some new outcome, okay? So for example, you have a patient with 2 children. Glucose is 40. I hope you just follow this one. 2 children, 40 glucose, blood pressure is 72, skin thickness is 79, insulin is 305, BMI is 56, pedigree function is 2.0, and then the patient is 40 years of age. So based on this feature, we can take the model so that it can predict the new features. And now if you run this one, we're being told that the patient is actually diabetic. So if you have a patient who is having 2 children, Her glucose is 40, blood pressure 72. Basically, this patient is diabetic. Basically, this is how you do your own prediction, and you can actually host this model in a cloud platform like Amazon Web Service or Azure platforms. And now people can start using the models in their mobile app or in web applications. So this is actually how we do classification. Just to do a quick recap, we say that with classification, we are mainly predicting categorical outcomes, okay? And now with regression, we are actually predicting numerical outcome. So now to finalize the classes, are there real-world application of classification? Yes, we can use it in our disease diagnosis, just like what we've done in our case study. Okay, so we can actually use this project to predict diseases like cancer, heart diseases, or diabetes. Okay, we can also use it to do risk assessment, to classify patients in such a way that you want to see patients that are in high or low risk for hospital readmission. We can use it for medical image analysis that is on healthcare, like MRIs. In finance, we can use the project to do fraud detection so that we can even classify transaction as fraudulent or legitimate. We can use it for credit scoring, so we can predict whether a borrower will default or a loan or not. And so on in retail and e-commerce, we can use it for churn, identify customers likely to stop using your services, sentiment analysis, and recommendation. For those people doing cybersecurity, you can use classification to classify network traffic as normal or malicious. You can use it for spam filtering and malware detection. Transportation, there are so many other ones. For example, traffic sign recognition, if you're building autonomous vehicles, accident risk prediction, route optimization. For those people who are working on marketing, you can use it for your customer segmentation, lead scoring, ad click prediction, and so many other ones, including environmental science, where you can do your specific classifications. You can work on pollution level prediction, such a way that you are classifying the air quality as safe or hazardous. And also you can work on it on disaster risk assessment in such a way that we predict whether a region is at risk of natural disasters or not. So basically, in conclusion, we can say that classification is a very powerful supervised machine learning technique, just like regression, mainly used for predicting categorical outcomes. So we have wide range of application, and the PIMA Indians diabetes case study is demonstrating its utility in healthcare for predicting diabetics risk and using some features like glucose and BMI. So by applying robust preprocessing, model selection, and evaluation, I can confidently say that classification models can actually deliver actionable insight that can improve our decision-making in real-world scenario. So with that one, I think this marks the end of supervised machine learning. Let's meet in our next class where now we want to explore the unsupervised machine learning technique. So that one, bye-bye.